Thank you very much, Michel, for this very kind introduction and introduction of CERN. Okay, then today I will speak about energy. I will start with some words about physics. Where are we? What is the importance of energy in physics? And I will do some quiz about what is energy for you and describing where are we with the energy in the world. Is it working? Yes. Okay. Our main challenge is difficult. I cannot see you, but a lot of light. The main challenge now is what we are trying to do at CERN in all the high energy physics is to look at the history of universe, to understand the first picosecond of the universe, to look at the Big Bang. We discussed during the dinner if we have to say why or not why, but we will discuss today about how. And we know that from the Big Bang now we have close to 14 billion of years with some dimension 10 to 28 centimeters, something that you cannot catch with our brain, but it is the situation. And I like to recall that what is the rules, that this is a size, the biggest size, 10 to 28 centimeters. At the beginning that we start to understand the things, it was 10 minus 32 things, and you can see this big spread of dimension. And by chance, human body, we are just in the middle. And today I put, as obviously Jim Besselsley, as the center of the universe. What else? Okay, then when you want to look at what the history of Big Bang, you can look at with in the cosmos, either with some detectors on the surface, as ALMA in Chile, very large telescope. Now there is a new one about detector on the ISS. By the way, this thing is the MIT project, but was built at CERN, and the control room is at CERN, and also Hubble now James Webb. I have to update things. There is one problem that at the beginning of the universe, during the first 380,000 years, it was so compact, so dense that nothing could escape. No photon or something like that. Then when you are looking backwards like that, you have this kind of wall, we call in our jargon Planck wall. You cannot see anything. You can see this kind of background and so on. Then we can do that. And it is an important period because this 400,000 years was a lot of physics, a lot of things with initially only energies, starting to have all these different forces. I have no time to discuss, and all the formation of the proton and neutron with quarks, atoms, molecules, and so on. And this, you cannot access to that if you are not reproducing the condition at the beginning for universe. Then, and I changed to be gender balanced, I put Odessa at the center of the universe. Then you cannot do that, and what we are doing with the accelerator is to have the condition at the beginning of the universe. We are not traveling back in the past, but we are creating in the big experiment a condition at the beginning of the universe. For example, in the one big experiment, ALICE, we are creating thousands of Big Bang per second to look at this Big Bang for a few picoseconds, but creating the things. This is the purpose of this large accelerator, large hadron collider, large because it's 27 kilometers, located 100 meters below the ground level, in which we have 4 big experiments. What it is here, Atlas and Atlas and CMS, which was the big multipurpose experiment. ALICE, exactly that, looking this soup of quark and gluons at the beginning of the universe, and LHCb, what is looking the difference between matter and antimatter. I have no time to discuss today in physics. We can discuss later if you want. But what I want to say is this: they are independent collaboration, larger than CERN, because you have physicists from all around the world: Japan, US, Canada, China, and Japan. But they are in competition. For example, Atlas and CMS were in competition for the discovery of the Higgs boson, but also in collaboration, and what we call co-petition. I think the notion to be in competition, but also to share the results. Why? It's not no more. I have a problem. Technology. Can you pass the next slide? It is frozen? Yes. What I want to say is that you have to be very clear in terms of theory. I was yesterday visiting Perimeter Institute just across the road when they're doing theory and so on. This, for the Higgs boson, it was initially in 64. You can see two papers. One paper was Mr. François Englert and Braut, and another was Higgs. Is 2 pages paper describing the theory that why we need Higgs. We discussed deeply with Michel yesterday, but I can explain what is the Higgs boson. But just to say that it was a 2 pages paper. After that, it was necessary to have, then this is individual ideas. You can have an individual ideas, but you need collective innovation to prove that. And the building of this large accelerator, detectors, computing, and it took almost more than 50 years to do the discovery. And after that, it was fast because it was an announcement the 4th of July 2012 in the main amphitheater of CERN with the 2 spokespersons. Fabiola Gianotti was the spokesperson Atlas. Joe Incandola was the spokesperson at CMS announcing the discovery. And 1 year later, the Nobel Prize to Mr. François Englert and Peter Higgs. Very rare to have only 1 year between the announce and the Nobel Prize. This photo is nice because it's a photo taken 4th of July 2012. It was the first time that these 2 gentlemen they met in person. Incredible, no? Okay. That's me. You recognize me? Yes, I was here. It was interesting because to assist us, young people, they spend all the night waiting at the door of the amphitheater to have the chance to have a seat in the amphitheater. I had the chance not to spend the night to have my reserve seat, but okay. What I want to say is that now come back to energy. What is energy? What we are doing, we are now breaking particles, and as I said, going back, what it is the condition at the beginning of a universe when all was energy. And you can see that on this table, that every time we were able to increase the energy of our apparatus, we discover new particles. The first was the electron. It was 1897 by Thomson with 1 electron volt. And after that, every time we were able, we were discovery with the boson 8 as LHC. And now we increase the energy of LHC from now 8 to 13 and soon to 14. And now what we are looking is new open question of physics. What could be the dark matter, supersymmetry? What could be, are we living in the 4 dimension or maybe 11 or infinite number of dimensions? What is at the beginning was only energy, matter, antimatter? Why we are living in a matter universe? Where is the antimatter? A lot of open questions. Then this is our knowledge now, standard models, explaining only 4% of the mass of the universe. Suddenly you become very humble, you understand 4%. You know, because the galaxies are turning faster and faster, further and further, then we know we have other mass, and we know that we can have, according to theory, 23-25% dark matter, 75% of dark energy. Then we can say that dark matters, and it is exactly for that we will want to continue and to build new accelerators to continue this race, this research of knowledge with all these open it's difficult. All these open questions, as I mentioned already. And for that, as Michel said, we are now looking, the LHC will operate up to 2040, 42, 45, 2045. And you have, if you want to have a next accelerator running in 45, you will need at least 25 years to design, build, and to put in operation. Then now the main accelerator is a 100-kilometer thing. So you can see this LHC seems tiny in comparison for this one. This 27 kilometers will be 91 kilometers at the end, passing under the lake and behind the sun. It's a very aggressive, very challenging project, and we are discussing with all around the world because US, Canada, Japan could be associated to this large project. Okay, now I will come back. Energy. What is energy for you? What is power for you? I said energy. What do you think? And another question. When you are thinking about what your last energy bill, what are you spending from your income in energy, total? Are you about your eating, cooking, transport, things? Do you know what you are? Very good. Good point, very good point. Then, are you spending 20%, 30%, 1%? And when I'm asking that to young people, and I'm asking second question, how much was your last rent? Everybody knows by heart, everybody, what you are spending. When you are paying for your smartphone, everybody knows. But normally, it's very difficult to give a number, what is your percentage of your income in energy. Okay, now I'm speaking just before the crisis. We'll come back to the crisis later. In average, in our countries, Europe, US, the average is 5%. We are spending around 5% of our income in energy, total. And it's exactly that because you can see this US energy expenditure as share of GDP is more or less 6-7% around that. And it was a question a lot of people, is it important to take care of around 5% of our budget? The same question that our brain is 2% of our weight. Is it important to take care of our brain? And I think if you are cutting energy, exactly what you said, we will be in trouble. We are in trouble. Okay, I cannot miss, because now it's true that this is the increase. We discuss the volatility and so on. This is increase in France, Italy, Belgium, and so on, about this peak of cost of megawatt hour. Okay, it was close to 80, we went above 1,000, now decrease with that volatility. I'm not an economist and so on, but no link with the production and so on. The same thing with the gas, coal, and oil. Exactly that, I think the definition of energy. Energy is a physics number, difficult to measure. It's impossible to measure directly energy. You need to have at least two things. If you want to have electrical energy, we have to measure voltage and current. If you want to measure potential energy, you have to know the weight and the height. These are difficult things. But in summary, energy is the ability to do work. And at the end, it's plant to grow, animal to think or move, machine, displace or fashion. And energy is a fundamental underpinning of life. And I think modern civilization is possible because we learn how to convert energy from one form to another form. Because something that has to be clear is the principle of conservation, that you are only converting energy in one form and so on, with some efficiency, but you are not creating energy. I think it's important because you can see when you are reading a lot of papers or journalists on the television, they are mixing what is energy and power. Always. People are saying what our consumption energy is 10 gigawatt. And windmill is producing the energy of 10 megawatt. And it's very important to understand that it is my only equation also, that energy is a power multiplied by a time. And I'm taking the example I'm taking with my son when he tried to explain. If you have a heater of 1 kilowatt, you are putting this heater in this room. You are switching on for 1 second, or you are switching on for 10 hours. the difference will be is still 1 kilowatt, but the energy and the heat of this room will change. But be careful when you are reading, especially from in renewable, solar, and windmill, everybody is speaking in megawatt and not in megawatt hour. We will come back later to that. Okay. The best energy converter, the former energy converter, is us. And you are eating a lot of things, and you are doing, as energy conversion, work and some heat. What can you do on average for a human, a good guy? He has a power of 10 watts in the arms and more or less 100 watts in the legs. Then if you want to produce energy, it will depend the time you will work. Imagine you are working with your legs 10 hours, you will have, okay, we can do that. Then 100 watt, 10 hours, you are producing 1 kilowatt hour. Then initially, a hard worker is between 10 kilowatt hours and 100 kilowatt hours per year. And your power, your energy you can put is basically you have to work every day and so on, 100 kilowatt hours. Then, and just to comparison, 1 liter of gasoline, is 10 kilowatt hours. 1 liter. Then you can see that you are working hard, you can produce around 10 liters of gas per year. If I'm thinking about a liter now, it was 2 euro in France or in Europe, then you are producing 20 euro per year. If I'm taking a low minimum salary of 1,000 euro per month, then it's 12,000 per year, then the ratio is a factor 600. Okay? I will come back to that. Everybody wants to say we want to come back to a sustainable world. Yes? The world was sustainable before 1850. We were using boat, the wind for the boat, we were using the horses, human, all the wind and so on. It was purely sustainable. And after that, now the world changed. Due to what? Machines. You have this big boat, this crane, large truck, I saw a lot on the 401 coming from Toronto, this crane and this press. But us, humans, we were eating agriculture and so on. Now what is the main ingredient of this machine is unfortunately coal, oil and gas. This is, if you want to think we want to come back to a sustainable world without any new energy, if you want to replace in terms of energy this truck and so on with this more or less what is the power, you will need in terms of persons this number. For example, if you want to transport the same quantity of materials that this large truck, you will need 4,000 persons. It was the case, building the pyramid, doing that, what a lot of persons. We replace that by machine. And this is exactly, this is the famous, the energy kilowatt hour per capita now in the world. And exactly, then to do the same work we were doing, to do more, we multiply the kilowatt hour per capita by a factor 200 in average and 600 in OECD countries. And when you are looking at the different type of energy, what is coal, oil, gas, and some hydro, a little of nuclear, and so on, we are adding every time energy. We can say we never did energy transition, except wood. Thanks to coal, we saved our forest. But we are always adding new form of energy. Now, this is in parallel, when we increase our consumption of energy, the world population increase with the same pattern. The correlation between the world energy consumption and the world population. What is also strange is the real GDP per capita, exactly the same matching. At the same time, we improve our life expectancy, the annual working per worker, and I took from yesterday a photo of the presentation of Jim Basili, the number one patent. Then we have to thank the new form energy, machine and so on, for the development of our society. But the price we pay is the number of the gigaton of CO2 we put up to now in the atmosphere. And all together, we are putting close to 40 gigatons of CO2 equivalent in the atmosphere per year. And if we are looking now, everybody is conscious, now is the concentration of the CO2. We can see this concentration is increasing because now we are close to 420 ppm in average. We were thinking in 2020, due to reduction during the COVID, but no influence of the concentration of CO2 in the atmosphere. It was completely integrated. What is also, because I had discussion with some policymakers in France, said, okay, we are very good electrical nuclear plant and so on, no problem, we are CO2 free and so on. What is true. But so one thing we have to say, first of all, is that when you emit CO2 in the atmosphere, I will say, a joke, but CO2 is sustainable. When it is in the atmosphere, in our atmosphere, it will take a long time to be absorbed by ocean, to disappear. Because when you absorb, it will be still 40% after 100 years, 20% 1,000 years, 10% after 10,000 years. Then every 40% of the CO2 we are emitting now, in 100 years, still will be in the atmosphere. And for what I'm saying is that if you are in a country very good and so on, but the air is mixing the CO2 around the Earth with more or less a time constant of 1 or 2 years, and complete mixing. Then we cannot be alone in our country. We have to think globally for the Earth. Okay, this is another curve, the same one about global primary energy consumption by source, more or less the same thing. Just to show also that in 2020 we did some reduction, but you can see the consequence on the GDP, but we did not learn because we restart more or less with the same slope. What is, we discussed that during the roundtable yesterday. For timing, 80% of production of energy is with fossil. 80%. We can say, several people said, okay, coal in percentage is reduced, is stable, but it still increases. In absolute terms, we are consuming more and more coal per year, more and more oil per year. We never decrease a type of energy. But now the challenge is really to reduce that. And I want to do, because I had some discussion also yesterday, why fossil is not good? Because when you want to transform energy from a fossil, you will emit CO2, because the fossil is the rest of the things and it's completely different, because this we have not to mix about ore, especially uranium and thorium, because they are not fossil. And if you want to transform energy, it's a mineral and you not emit CO2. And this is a very important notion. Now, as I said, we emit collectively 40 billion of tons of CO2. It's important to see Europe, for timing, is not reducing but stabilizing, but is not helping globally the total world. And if we are good, if we are not able to transfer technology or to help, it will not solve. As I said, every 1 or 2 years, the CO2 will mix. Then we have to work collectively to have a global strategy if we want to go to a solution that in 2050 we are carbon neutral free. I'm saying climate change is moving fast, we need to move faster. And this, I think, for me, the only solution is to have a coherent, solid R&D, which imply strong and long-term political support. And I will explain several things now, if I still time. Obviously, renewable, what you call renewable, I will say CO2-free in terms of windmill. I took that myself a photo when I was in California. This is a big new solar farm. Nestor should know now is one of the two for Stanford University. I will come back to that. This is Ivana solar farms. I took myself between Nevada and California. This is fantastic. The problem of this renewable is storage. But now there is a big progress, I think we have to say. In the last 10 years was a large progress. And mainly I want to mention Yves Chui, that from Stanford University, that he did a lot of progress in terms of battery, in terms of density, number of cycles, recycling, and so on. And this is exactly, and now, for example, they developed this 1 megawatt-hour storage in one container, which is a fantastic achievement, but it's still 1 megawatt-hour. They want to go to gigawatt-hour, terawatt-hours with this elementary brick. I think for me, this priority in terms of, and this is due to nanoparticles, new technology, nanoparticles, and a lot of things coming from physics. And I think it's important now for the battery, especially for cars, for transport, is the number of cycles, the safety, and more important, we discussed also during the bar rooms, is a cradle to grave in the recycling. And now, as you can see, this is not with lithium, but the lithium battery for cars, they can recycle up to now 95%, and they are going to close 99 to 100%. And after the lifetime, you could disassemble and with energy to rebuild your battery. And this, for me, is a very important concept. Okay. In terms of storage, we have progress every day. I took that because it's a breaking news. It was in last 7th of September, where they started a new construction of 170 megawatt hours, which is a large storage. But we have not to forget, I mentioned that, the annual world consumption is 140,000 terawatt hours. And this is only 1 part per billion of our consumption. We have progress, but we are far to say that solar energy and wind energy we can store for the global consumption. I cannot miss this photo has shown that now I think is very good progress in terms of example of Stanford University. Sorry to mention so far Stanford, but it is now is a 100% renewable energy, what is very good. The situation of Stanford in California is particular, but it's very good to have that. And also in California, there are a lot of projects, a good use of solar energy. For example, with this solar over canal alone, that it could go up to 13 gigawatts. After that, we will have to compute, let me say, 20 to 30%, multiply the number of hours to get the energy per year. Okay, this once again, this is more and more windmill and so on. In global wind power capacity is now close to 900 gigawatt in 2021. Once again, when we are looking, all these things are in gigawatt, but when you are looking in US, they are saying that you produce close to 35% of the time, and you have to multiply this number by the number of hours per year and divide by multiply by factor 0.03. In Europe, we are less because different conditions. We are at 15%. And it's very important when you are looking the number, comparing the number of the different sources of energy, not to look at once again the power, but the energy. Okay, now I think I have to speak about fission. Fission is how you can break heavy atoms and breaking that produce energy. And this, it was a long history from the end of the Second World War with the different generation. Now we are in generation 3. I have no time to describe, and we are thinking to go to generation 4 with fast neutron. And I think this is a good source of energy, CO2-free, not without problem. Everybody knows all the accidents in 3 Mile Island, Chernobyl, and Fukushima. We have to look at all the consequences. But now, I think with the technology, we have more and more safer, security and other things. And I think new things is how to have treatment, nuclear waste management. It's not only management, but how you can use the nuclear waste as a fuel for the new generation of fission. And this is definitely thanks to the physics that we can do that. Then now we are speaking more and more about a small modular reactor or nuclear battery. I was with people from MIT, and now they are thinking to have this battery that you can put on a truck, and you can do, and you have a lot of projects around the world of this small nuclear battery. You can build in 5, 6, 7 years, and you can think to now to have some fabric with their own independent energy with a nuclear battery. And there's a lot of R&D, a lot of startup working on that. But one thing I want to mention today, because I'm part of this startup, is called Transmutex. It's the idea to transmute the nuclear waste. The idea is to put in a reactor the nuclear waste, to have a proton accelerator, to accelerate a beam, to smash the beam against a spallation target, to get first fast neutron, and the fast neutron will transmute the nuclear waste. Then you are using your waste as energy, and you divide the lifetime, long lifetime, 300,000 years by a factor of 1,000, and the volume by a factor of 10. Then now there is some demonstrator. Then now we are in the phase of demonstration, and hope to have the support of the policymaker to go to this new generation of nuclear generation 4, where you can really minimize the storage and minimize the lifetime of the storage. Last but not least, fusion, certainly something that we can think after in 50 years. We know fusion is existing. The sun is pure fusion. All what we are using, solar energy, is fusion, because initially is this really the fusion of helium, deuterium, tritium in the sun. And now there is a lot of development, thanks also to physics, to development R&D. The main project is ITER in Cadarache in France, but it's a worldwide project and in construction. We had discussion about the cost yesterday, because it seems enormous. The cost of ITER up to now is 20 billion of euro. Is it expensive or not expensive? 20 billion of euro over 25 years is less than 1 billion per year when you say paid by US, Europe, Japan, China, Russia, Korea. I'm missing one. No, 7 members. Less than 1 billion for humanity to try to discover new form of energy. I think when you said it's too expensive, we have to discuss that. I think humanity, we have to invest for CO2-free energy in the future, and less than 1 billion per year is not expensive, for my opinion. And now you have more and more startup working, as I discussed with CFS coming from MIT. We are starting a startup also in Europe to look at how we can accelerate the technology for fusion. China is working on this fast track. Then I think a lot of things is boiling now in this domain. Okay, I will go to my conclusion. In terms of strategy, what in my personal view, first of all, we have always to go to sobriety, to try to reduce. Living for 6 months in US, I think there is room for improvement. Looking also the cars and the trucks in front of the road, I think there is room for improvement. When I was in US also with the air conditioning, with the door completely open and so on, there is room for improvement. But okay, in Europe we have a lot of things to do. But after that, we have also to look at efficiency, recuperation, life cycle, and we have to build that from the design. When you are designing, and I pushed all my colleagues when we are designing accelerator, you have to think from the beginning how you will recuperate all the materials you are putting in your apparatus. Energy, we can say mainly is 1/3 industry, 1/3 it is in transport, and 1/3 in households. Household challenge, but there is a lot of opportunity to do that. It's just investment. We know how to build now buildings, house with a positive energy. The more difficult is transport, especially trucks, boats, and so on. Car, we are going towards electrical cars. Then I think we have, if you want to reserve something about oil, is for transport and reducing slowly the things. I think we need massive investment in new technology, renewable, to have, especially in storage, but also in windmill, superconducting windmill. There are a lot of things to do that. But we have not to escape. It's a big debate, I know in Germany, but also in France nowadays, in Switzerland, about fission. I think it will be more than difficult not to have fission in the next 30 years if we want to reduce this 80% of CO2 fossil. We have to go, I think, to, or if you don't want to come back to in 1850, and we have to go into invest in technology about waste transmutation, subcritical reactor, SMR, nuclear battery, and also to inject for the next future about fusion. I will say also it's very important, I think every organization, everything has to do, we did at CERN, is to measure what your consumption. And we be aware of our consumption in order to limit and to mainly limit our CO2 emission. If you are not measuring, you don't know. I would love to have myself, my CO2 emission at every time I'm buying an object. I would love to say, okay, how many kilos of CO2 can I compare? If you are traveling, now if we can do, but look at your budget, but individually, but I think it's very important to do that, and now is a method for any organization. And this is very important because it will be that. One thing I want to say, especially for young generation, then the time constant of the climate is long. It's 30 to 50 years. Then what it will be the main challenge, it will be that if we are doing a lot of effort, we are reducing CO2, zero, we will see only the benefits in 30 to 40 years. This is a very difficult thing. When you have somebody speaking about the kids or a baby, if you are asking to a baby to do something, you will see the consequence in 10 or 20 years. It's very difficult to improve yourself. But this is, we have to pass a message. The time constant is huge. Okay, I think I want to finish with two quotes. I like that. In nature, there are neither rewards or punishment. There are only consequences. And people said we have to save the planet. We have not to save the planet. We have to save humanity. I'm sure if we are continuing to have a lot of CO2, where we have an increase by 5-6 degrees of the average temperature, we will disappear. But the planet will stay for the next 5 billion of years. The future of humanity is not planned because it depends on it. Bergson, I think so. And I will finish by physics is beautiful, and I hope we can demonstrate it's useful. Thank you very much.
Thank you so much, Frederick. This was a wonderful presentation. I love that you finished the background of the last slide was the same as next NIS 100 Symposium, which we use all over the place. It was Frederick in the middle of the slide going like this with the galaxy above him. It's my favorite
It's
photo.
the beauty of physics.
It's the beauty of physics, that's right.
No, it's not beauty. It's the beauty of nature, and it is why I start to do physics. When you look in the sky, say, oh, I want to understand that.
And we will have also with Frederick a breakout session today at 12 on disruptive technology in energy and the green energy transition. So another thank you to Frederick.
Thank you.